So, hey everyone, today we're going to solve this number of black blocks problem. So basically, first you're given m and representing a zero index n by m grid. So basically, is m is the height and then n is the width. So we are also given a list of coordinates. So each coordinate will have the position x and y. So it indicates that in this particular position, the color of this cell in the matrix is black. So when it is not defined in the coordinates, it means that the coordinates of the cell are white. So now a block is a 2x2 submatrix of the grid. And then what we want to know is that what is the number of blocks that contains exactly I black cells for every subgrid inside the matrix. For example, let's take a look at the first example. So m is free, n is free, so the height is free and the width is free. That's why you can see this is a 3x3 matrix. And the coordinates is 0, 0. So that's why you can see the only black cell is the top left one, 0, 0. So the output answer, the first one is 0 index. So this means that answer 0 is free. So it means that there are exactly free subgrid that has 0 matrices. So as you can see here, this one starting from 0, 0, this has exactly 1. So this is what this one comes from, and this one is 0, and then this one is 0, and this one is 0. So in total there are like 3 of them, they are empty, and 1 of them are 1. So that's why this is the first answer is 0 and the second is 1. So also you cannot find any submatrices that have 4 or more or 3. So because we only have one black cell, so that's why for the other things we just have 0, 0, 0. So let's take a look at the example 2. Again, the m is free and n is free. So that's why we have this 3x3 matrix again. And then the coordinates is 0, 0, 1, 1, and 0, 2. So again, inside the coordinates is the black cell. So let's take a look at answer 1 actually. So they are actually saying 2 of the 2x2 submatrix are having exactly 1. So from what I see here is this one, the bottom right, and then the bottom left. So these are the 2 submatrices that are having exactly 1 block, exactly 1 black cell. So as for 2, so one of the submatrices that are having exactly 2 black cells are the top left one, and this one, the top right one, are having exactly 2 black cells. So that's why we are having this 0, 2, 2, 0, 0 answer. So that's pretty much all of the problem description. So how can we solve it? One way to solve it is to try to think of every coordinate inside the coordinates as the top left. For example, I would treat everyone as the top left, and for example, this one are the top left one. The top left grid, and I would treat this cell 0, 0 as the top left, and then you can see this is actually have the total sum of 2. So it is added as 2, the answer 2. And then we can also check this one as the top left, but hold on, it cannot actually be the top left. So that's one thing that we have to check, is that it is not always possible to treat the cell as top left, because if I treat this particular cell as top left, the one with the on the top right, if I treat it as top left, we actually don't have to position here to make it as a top left. So that's why we cannot make this as a top left. As for this one, if we treat it as the top, as for the one on the 0, on the 1 1, on the position 1 1, if we treat it as the top left, and we can get something like 1, because the total number of cells, the total number of black cells here are just 1. So that's why we can kind of calculate all the things. But you may be asking, what if the black cell, the cell that the top left is not turned on, but we also want to calculate it? So for example, let's take a look at the submatrix on the top right. So this top left is not turned on. So in my loop, I didn't consider that. So that's why there is an issue. That's why we also have to iterate every other position, assuming that it is the bottom left. So if we assume this is the bottom left, we also have to check that the top left, according to this bottom left, the top left is not counted already, because if it is counted, and we will be double counting. So otherwise, we can just count it. Of course, we cannot just stop at assuming the top left and the bottom left. We also need to assume for the bottom right and the top right. And also, of course, if they are considered previously, then we just have to continue, just in order to prevent the overcount. So that's pretty much the idea of the problem. So in this way, we can just iterate every coordinate 4 times. So because 4 times n is still n, so it turns out that the answer, the time complexity of the solution will be just O to OX, where X is the length of the coordinate. So yeah, that's pretty much all. And let's jump into code implementation. I will be writing in Python, but other languages should be similar. So first of all, we have to initialize the answer as 5. So as we explained before, the answer must be 0 within 0 to 4, because that's, if you think about this submatrix, the possible numbers inside of a submatrix can only be 0 all the way to 4. So that's why the answer will never be larger than 4. That's why having 5 is already enough. So we are gonna initialize that at the beginning. Then we have to initialize a hash map, which is black. So basically, this is just a 2D hash set. So if it is 1, if it is inside the coordinates, then I will return 1. And if it is not inside the coordinate, it will return 0. So I did this for the default tick, is a way to just return 0 when it is not specified. specialized. So in this way, it's just easy for me to calculate the sum later on. So then I will initialize the top left, top right, bottom left, and bottom right. So it just means that, for example, for top left is how many coordinates can be top left, and how many coordinates can be top right. So as I explained earlier, not all of the cells can be top left. For example, if it is already on the rightmost column of the matrix, so it cannot be top left because there is no room for it to have a 2x2 matrix starting from that particular cell. So now we have to iterate each coordinate R and C. By the way, I'm not using the notation N, M, and XY. Instead, I will use height and width for H and W, and R for row, and C for column. So I think usually in this kind of problem, just use this naming just makes more sense to me with compared to just the X, Y, and N, M. Sometimes N will be the height and sometimes M will be the height. So it's just a little bit confusing for me. So usually I just like to change them to height for H and W for width, and then R for row, and then C for column. So anyway, just keep going. In this here, we just add this coordinate is black, just add it to 1. And then we're gonna check if it is possible to be a top left. So the way we check it is that if there is some room on the right hand side and there's some room on the bottom, then it can be a top left. And then we also check if it is possible to be a top right. And then also check if it is possible to be a top left and it is possible to be a bottom right. And then first we're gonna check for each possible top left. And then we're gonna check the sum of this subgrid. So basically this 1 means the top left is the R and C. So it has to be 1, otherwise it won't be inside the top left at all. And then we're just gonna check R plus 1 means at the bottom. So it means the bottom left, and this one means the second one means the same row but on the right hand side, so it should be the top right. And then this one is R plus 1, means it is the next row, so it's the bottom row, and C plus 1 is the right hand side, is the bottom right. So basically I just get the sum of this subgrid if R and C is the top left. So and then we store it inside S, we represent the sum of the matrix. And then we will just have our answer S plus equals 1. And then we have already considered everything that starts at the top left. But as I previously mentioned, sometimes in the subgrid, the top left might be off, but the subgrid is still part of our answer that we cannot ignore. So that's why we have to consider all 4 possible position of the subgrid. So let's now consider top right. So again, we're gonna check if it's black, R and C minus 1. So now R and C is the top right. So C minus 1 is actually just means it is the top left. So it basically means that I'm trying to treat R and C as the top right, and then I'm going to check for this subgrid. If the top left already exists, then it means that it's already considered in the previous for loop. That's why I'm going to ignore it. And also, after that, and I'm going to do the same thing to check for the sum of this submatrix, and then store it inside nest. And then I'm going to add to the answer. And then similar for bottom left. But now this time we want to check if it is considered in the previous 2 for loops. So if it is already considered, then we continue. Otherwise, we will just try to add the sum of it again. So probably I have to mention is the S now is only considered C plus 1. It is because we know for sure that top right and top left of this particular submatrices will be 0. It's actually useless to consider that. So because if they are true, they will be already calculated in the previous for loop. Then if they are already calculated in the previous for loop, then I will just continue here. That's why I don't have to add the other things. So in this case, because we already considered the top right and the top left, so if they have something, then I would have already calculated their value already. So that's why I only care about the bottom right, which is the only one that has not been considered yet. So again, we just answer S plus equals 1. And then the last loop is considering the bottom right. So if it is considered in the previous 3 for loops, then we're going to ignore it. Otherwise, the only thing that we can add is answer 1. And then we plus equal it. So lastly, for the answer 0, 1, it basically means that every possibility that we have considered will be inside the answer, no matter it is 2, 3, or 4. They will already be in the answer. So how many total possible subgrid inside an H times W submatrix? So the answer will be H minus 1 times W minus 1. Because if you think about it, if you just think about for every top left of the submatrix, so if it starts at the very last column, or if it starts at the very last row, it cannot be top left because there's no room for it for a 2x2 matrix. That's why for an H times W matrix, there can only always be H minus 1 times W minus 1 2x2 matrix. So this is the total possibilities and minus all the things that we have considered. So it means there is nothing on the remaining submatrix. So this is why this is 0. 0 means there's no black cell on that submatrix. So at the end, we can just return the answer. So let's try to run this. Okay, so that's pretty much all for the code implementation. I hope that helps. That's all.